Okay, so this is a lesson on significant figures. You'll probably hear them called Sig Figs. So the first question is, what are they? What are significant figures? And the quick and short answer is that Sig Figs are a quick and dirty way of treating precision. So in other words, they're a way of telling you how sure you are about your measurements. For example, I'm about 6 feet tall. I wouldn't tell people that I'm 6.0598769 feet tall because I'm not that sure. I know I'm about 6 feet, so that's all I say I am. Now, how do they work? Well, they work by convention. When you make a measurement, you only record the digits you're sure about, plus one that you guess. So for example, let's take this box. If we want to measure the length of the box, let's put the ruler up to it. Well, it might be hard to see over the screen, but I'm a bit closer, and I can tell, well, it's definitely bigger than 4. It's definitely bigger than the 0.2, and it's somewhere between 4.2 and 4.3. So I'm sure about the 4, I'm sure about the 0.2, and I have to guess somewhere between 0.2 and 0.3. Well, I'm not too sure. Looks like it's about halfway between, so I'll guess it's 4.25 centimeters. So the convention is, if somebody else came along and looked at my measurement, they'd know for sure that I was sure about the 4 and I was sure about the 2, but I was guessing the 5. So they wouldn't put too much confidence in that. All right, let's go ahead and measure the width. So we're going to put our ruler up to the width, but uh-oh, what happened? A cat got in the way. And now we can't get our ruler right up to the edge. So this kind of stuff happens all the time in physics. You can't get the most accurate or the most precise measurement you want because something's in the way, or you can't get your ruler up to it, or it's moving too quickly. So sometimes you have to take measurements that aren't the perfect measurement. So this is about as close as I can get the ruler, and now I'm less sure about my measurement. I know it's at least 2, somewhere between 2 and 3, but I'm not sure exactly if it's 2.1 or 2.2, so I'm sure about the 2, but I'm going to guess the next one. I'll guess it's 0.1. So I'll say this is 2.1. So because we weren't able to make as precise a measurement because the cat got in the way, we wind up with less figures, less significant figures. Alright, so that's the basics of it. Let's say that we now want to perform a calculation on this. For example, we want to find the area of this box. Well, that involves the length and the width. We all know that area is length times width. So 4.25 times 2.1, figure that out, that should be 8.925 centimeters squared. But if you think about that, that doesn't make much sense. We've taken 2 measurements, one had 2 significant figures, one had 3, and our answer seems to have 4. In other words, by doing a calculation, we've increased the precision of our measurement, which doesn't make sense. So the rule we have here is we only keep the minimum number of sig figs from each of the numbers in our calculation. So in this case, this one had 2 sig figs, the length had 3, so our answer should only have 2, which means we'll round it to 8.9 centimeters squared. So this brings up our first rule. I'll slide it right here. When multiplying, dividing, square rooting, squaring, or raising to any exponent, you want to keep the lowest number of sig figs. Alright, so second job, we want to calculate the perimeter of this square. So that's going to involve adding 4.25 plus 4.25 plus 2.1 plus 2.1. And if we add all that up, we find it comes to 12.7. So, and we need our units, of course. So the first thing you might think to do is, well, we only had 2 sig figs as our minimum, so should we round this to 2 sig figs? Should we round this to 13 centimeters? Well, actually no, because for addition and subtraction, there's a second rule, a different rule. When you're adding or subtracting, you want to keep the least number of decimal places. So, in this guy, there were 2 decimal places, 0.25. In this one, there's only 1. So our final answer should have only 1 decimal place. And as it happens, it does. 12.7, the 7 is in the first decimal place. So we don't have to round this one at all. Okay. So that's pretty much the basics of sig figs, but there is one little thing that messes people up all the time, and that's zeros. So we'll call this a little complication. The problem is, zeros are numbers, but they're also something called placeholders. And I'll give you an example here. Let's say we take a 2 centimeter line, but we want to convert those 2 centimeters to millimeters. All right, well, hopefully you can do that in your head, but 2 centimeters is the same as 20 millimeters. But here's the thing, it's the same measurement. We've got 2 centimeters, we only have 1 sig fig, but just by converting units, somehow it seems like we have 2 sig figs, and that can't be right. So the deal is, the 0 on the millimeters is acting not as a number, but as a placeholder. It's there to show that the 2 is in the tens place. So the 0 here is not significant. Okay, let's look at this another way. Imagine that we wanted to measure the length of this rubber eraser. And imagine that we used this ruler. But for maybe there's a cat in the way or something, we can only keep our ruler this far away. So it's not going to be a very precise measurement. If you can see, the increments on this ruler are 0, 10, 20, 30, so they go up by tens. And based on this, the distance, it's tough to get a very precise measurement. I'd be guessing in the tens digit. I'm not sure, it could be 80 or it could be 90. It might be almost 100, although that's probably a bit long. So if I had to estimate the length of this rubber eraser, I'd guess 90. But it's really the 9 that I'm guessing. I'm not sure about the 9, I'm guessing 0. I'm guessing the 9. That means that this is my last significant digit. This is my guess. The 0 is only there to show that the 9 belongs in the tens place, to make it 90. So this doesn't have 2 significant figures, it only has 1. So sometimes when zeros are at the end of a number, they can't be considered significant. But let's look at another case. What if there was nothing in the way, and we were able to get our ruler all the way up close to it? Now I can see with a little bit more precision that it is actually right around on the 90. Now it might be 91, it might be 92, it might be 93, but I'm very sure about the 9. The 9 is no longer a guess. The thing I'm guessing is the next digit. To me it looks like it's right on the 0, so I'd actually write it 90. But now this gets confusing, right? Because before, if we wrote 90, it only had 1 significant figure. Now if we write 90, we want it to show 2, because we're sure about the 9 and we're guessing the 0. So in this situation, when you want to show somebody that the 0 at the end is significant, you put a decimal place at the end. So when there's a decimal place at the end, both digits are significant. when there's no decimal place at the end, the 0 at the end is not significant. So based on whether it's a placeholder or a number, the number will be significant or not. So here's a list of rules. This kind of sums up all of the times when zeros are significant. They're significant when they're sandwiched between two other significant numbers. I'll give you an example. If we have 306, what's happened here is we're sure about the 3, we're sure about the 0, and we're guessing the 6. So we say this has 3 sig figs. They're significant when they're at the end of a number after a decimal point. So let's say we have 306.000. We know that these zeros at the end are significant because if we got rid of them, we'd still have the exact same number. So clearly they're not there to be placeholders. The only reason we put them there is to indicate more precision. So if they're at the end of a number, they're significant if they're after the decimal place. So this number would have 1, 2, 3, 4, 5, 6 significant figures. And it would be indicated by this that we were guessing in this last decimal place. They're also significant if they're at the end of a number and followed by a decimal point. So if I took 50 with a dot, I know that I'm sure about the 5 and I'm guessing the 0, so I've got 2 sig figs. I'll show you some places where they're not significant. For example, if they're at the beginning of a number, so 0.0005, these guys here are just placeholders. So 1, 2, 3, 4, these 4 zeros are not significant. This has 1 sig fig. And they're also not significant when they're at the end of a number and there's no decimal place. For example, 6,000, and 50. We're sure about the 6, we're sure about the 0, we're sure about the 5. Oh, I'm sorry, we're guessing the 5, and the 0 is just there as a placeholder. So this has 3 sig figs. So sig figs are the most basic way of keeping track of precision. As it turns out, they're not the best. Sometimes when you carry calculations, the fact that you have to round them will eventually mess up your calculations, or at least reduce the precision of them. So next lesson we're going to learn a far superior way of dealing with uncertainty, or dealing with precision, and those are uncertainty ranges. And that's the preferred method in physics. And that's the end of this lesson.